In this video, I'll be looking at page 6 and 7 on the lesson for today. So now we're going to talk about, is there a connection between mutually exclusive, two events that cannot happen at the same time, and independence? So if we look at these two events, event A, the person is male, event B, the person is pregnant. These events, hopefully you understand, are mutually exclusive. You can't be male and pregnant, I guess, as far as I know. Are the events independent? Does knowing that one event occurred change the probability of the other event occurring? Well, if I know a person's male, then I know that they are absolutely not pregnant, where overall the chances or the probability that somebody is pregnant might be, I don't know, 3% or something like that. So these events are not pregnant, or these events are not independent because the probability of being pregnant given male is 0, which is not equal to the probability of being pregnant, or vice versa. What do I mean vice versa? The probability that you're male given you're pregnant doesn't equal the probability that you're male, because this would also be 0. Basically, mutually exclusive events are never independent. Mutually exclusive events cannot be independent, because once one happens, the other cannot happen. All right, for learning objective 4 and 5, now we're going to take this multiplication rule and calculate some specific probabilities using tree diagrams. I was going to do this game with you today, but obviously I'm not there, so we can't. Basically, I was just going to go through this scenario. You have 5 cards, 2 aces, 3 kings. People choose a card, don't replace it, choose a second card. If you get a pair of aces or a pair of kings, you win. If not, you lose. So I was going to have us run 5 trials, probability of winning this game, but not going to happen. So let's look at this theoretical probability. So we have 2 aces out of 5 cards. We have 2 aces and 3 kings. So how this is going to look is the probability you pick an ace first is 2 out of 5. Given that you picked an ace, the probability the second card is an ace is now 1 out of 4. Because you took the ace out, there's only 1 left, and there's only 4 cards left. Probability that the second card is a king, all 3 kings are there out of 4 cards. Now, if I want the probability that the first card is an ace and the second card is an ace, I'm going to multiply these probabilities. These are not independent events, because I can see the probability change. And I'm going to get 2 out of 20, or 10%. If I want the probability the first card is an ace and the second card is a king, again, I'm going to multiply these, 6 out of 20. So what I'd encourage you to do, try and pause the video here and fill out the rest of the tree diagram. The probability that my first card is a king would be 3 out of 5. Given that you picked a king first, now what's the probability you get an ace? Well, both aces are left out of 4. Both kings are left out of 4. Or there's only 2 kings left out of 4 cards, so this is going to be 6 out of 20, 6 out of 20. So you win the game if you get a pair of aces or a pair of kings. So ace-ace is a winner, and king-king is a winner. So 2 out of 20, 6 out of 20. I can add those because they're mutually exclusive. I can't get ace-ace and king-king if I play once. So 8 out of 20, or there's a 40% chance that you win this game. So hopefully you don't want to play this in the long run. You understand that. Maybe in the short term, you're likely to win more often, but over the long run, it's going to trend towards that 40%. Now, we're going to ask a conditional probability. What is the probability the first card is a king, was a king, given, there's that keyword, given the person won? So probability king first, given they won. Well, we know the probability that somebody wins is the 8 out of 20. And the probability they get a king first is, and they won. The probability they get a king first and they won is 6 out of 20. So let me kind of talk through this again. This formula is probability king and 1, or intersection 1, divided by probability that they won. And this is a formula that's on your green sheet. I think I have one right next to me. Yes. I never go anywhere without this. Boom. All right, probability of A intersection B divided by probability of B, knowing that that is given to us. So I'm just looking at that. The probability of the intersection that they got a king and 1, 6 out of 20. And the probability that they win, 8 out of 20. You divide those, you're going to get 0.75. So there's a 75% chance if the first card was a king. I'm sorry, given that the person won, the first card is a king. So summarizing this general multiplication rule, we're using it, but we're never really doing this rule. Like, we're never writing out this formula and thinking about it this way. Can you? Yeah, I wouldn't advise it. When we're using the tree diagram, this is exactly what we're doing. If I want the probability that the first card is an ace and the second card is an ace, I'm taking the probability that the first card is an ace times the probability that the second card is an ace given the first card is an ace. I'm multiplying these two probabilities across the branches to get this. Okay? If the events are independent, then the probabilities aren't going to change. Here, the probabilities change, and that's fine. This general multiplication rule will work for all events, whether they're independent or not. Okay? If A and B are independent, we talked about the two ways to prove an independence here. Tree diagrams, what you'll see here, you have an event, not the event. And then you have the second layer of the tree diagram. These are all your conditional probabilities. These are your conditional probabilities. When you're all done and you multiply across the branches, you have to have these sum up to 1. And then we talked about the probability of at least 1. So let's look at this last part. The probability of, you have some beads in a jar, 8 red, 12 blue. If they're selected at random one at a time and not replaced, what's the probability of selecting 2 red? So we want the probability of selecting 2 red. This means there's 8 red out of 20 total, times, given the first one was red, what's the probability the second one is now red? Well, there's only 19 left. We took 1 red out, 7 out of 19. Whatever that is, I have no idea. 3 red is going to be very similar. Hopefully you can pause this here, do this calculation on your own. It'd be 8 divided by 20 times 7 divided by 19 times 6 divided by 18 is something, whatever that is. So this is an application of the general multiplication rule, but we're never like writing down this formula and doing this. What you need to recognize is this is the probability of red. This is the probability of red on the second, given the first was red. This is the probability of red on the third, given the first two were red. So that's where the application comes in. All right, the last part of this lesson in this video that I want to make, I know there's a few more examples in the lesson, is this question. I'm going to skip 8 and go to 9, because I think this is a good application. I'd like to talk about the COVID question together later. All right, many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes there's false positives where it says the woman has breast cancer when she really doesn't, or a false negative when it says that the woman doesn't have breast cancer when she actually does. And you can argue pros and cons for each of those scenarios. So say we have this information. 1% of women over age 40 have breast cancer. So probability of somebody having breast cancer of women over 40, 1%. For women who have breast cancer, this is given. And this is going to be key. For women who don't have breast cancer, that is also given. These are going to be conditional probabilities. All right. A randomly selected woman age 40 or over from this region tests positive for breast cancer. Find the probability she actually has it. So This is what I was talking about earlier in the lesson. This is a conditional probability. She tests positive. That is a known fact. That is a given. What's the probability she actually has this? So it's the probability that she tests positive given she has breast cancer. That's what we're trying to figure out. I don't have any information right off the top that can help me answer this quickly. I know given somebody has breast cancer or doesn't, what the probability of a false negative or a positive test, but that's backwards. So I need to utilize a tree diagram here. And when I start this, I need to start with what's not a conditional probability, what's not given. And that's this 1% of women age 40 and over have breast cancer. So let me see how I do that here. Okay, so I have 1% of women over 40 in this region have breast cancer. The other 99% don't have breast cancer. You could write the words, not breast cancer. I'm just using the notation for complement. Now, given that they have breast cancer, for women who have breast cancer, the probability of a negative mammogram is 3%. So the probability that they get a positive test, the probability that they test negative. They told us the probability they test negative is 3%. The probability that they test positive is 97%. Okay, so 3% of the time, they're going to get a false negative. That's what this is. They have it, but they tested negative. Given that they don't have breast cancer, the probability of a positive is 6%. So 0.06, they're going to test positive 6% of the time. They're going to test negative 94% of the time. Remember, all of these are conditional probabilities. This 0.97 is the probability that someone tests positive given they have breast cancer. These are all conditional probabilities. Okay, so if I multiply across the branches, I'm going to get 0.0097. That's the probability that they have breast cancer and they test positive. If I multiply across these branches, 0.0003, that's the probability they have breast cancer and they test negative. Same idea here, 0.0594, probability that they don't have breast cancer and they test positive. And then 0.9306, this is the probability they don't have breast cancer and they test negative. So you could see the majority of the probability is coming from women who don't have breast cancer and they test negative. I can do a quick check to make sure these add up to 1. They do. This is 99%. This is that other 1%. Okay. So now how am I going to use this tree diagram to help me answer this question? That's what I'm trying to do. So I'm going to take this probability breast cancer given test positive. Instead of TP, I use positive and negative, so I'm just going to switch it. Now I'm going to go to my green sheet and think about this formula here. So this would be the probability that they have breast cancer and they test positive divided by the probability they test positive. Okay, so looking at the options from the tree diagram, there's 4 options. Let me get my face out of here. In 2 of the 4 options, they test positive. Here and here. They're mutually exclusive. The women had breast cancer and tested positive or didn't have breast cancer and tested positive. So if I start with the given, the probability that somebody tests positive is the sum of those two, 0.0097 plus 0.0594. Out of that, the probability that they had breast cancer and tested positive is just the 0.0097.